Today we're just going to talk about the very basics of how we're going to do linear regression in R. Let's just demonstrate with an example. I've made up a widget factory, and the widget factory is just a fictional factory that makes fictional things, widgets. And let's say these widgets are manufactured in batches, and depending on the size of the batches, it's going to take us a sort of different amount of time to make them. Okay, so let's look at the batch size here. So this is the size of the things we need to make, the batch size, and Y is the amount of time in man hours, person hours that it takes to make these widgets. Okay, totally made up data just to sort of have a fairly easy example to start with. Okay, and of course, like, we could plot this. We all know how to plot this. This is something we've probably done in other software, or we've done by hand. And we're going to plot man hours against batch size. So that's Y against X. So the man hours is on the Y axis, the batch size is on the X axis. And all I've done is I've plotted this data here on this plot here. Okay. And it's fairly clear that a straight line, so if I draw a straight line up here, it's going to be a fairly good representation of some kind of average trend of this data. Okay. So, exactly how we fit this data. Okay, so how do I say that it's this line as opposed to, perhaps this line? Well, look, one good way to do is say, look, my original line looked better, so we kind of know instinctively what fits and what doesn't fit. But actually we're going to do this by something called least squares regression. And least squares regression is just a statistical way of finding the line that fits best. Okay. In practice, what I do is I have some set of data here. So let's say I'm doing it on a very simple set of data here. I'm trying to draw a straight line through those. What I'm going to do is I'm going to drop a load of vertical lines from the lines to the points, and the straight line that fits best is the line that minimizes the sum of the squares of these distances. So this is least squares. Okay, and we won't go into that too much here now, but just for now, just trust, if you haven't seen this before, that there is a way of determining which line looks best, which line fits well of all the straight lines I could draw. So it turns out for this example, because it's artificial, that the straight line is exactly Y equals 10 plus 2x. Okay, so this is my line of best fit. And what this means is that the man hours is 10 plus twice the batch size. So let's look at an example here. Let's look at this point here. Okay, and if I drop a line down here and I drop a line sort of somewhere over here, then the man hours is about 150, and it's going to be 10 plus 2 times the batch size, which is going to be about 70. Okay, so this kind of fits in with my overall equation of the straight line. And what does this mean? Well, look, okay, I could interpret this as for every batch of widgets I make, it takes me 2 times the size to make it. So 70 takes 140, but maybe I have some time setting up the factory, which takes 10 hours or something like that, which gives me 150 hours. Okay, so there's initial cost. Even if my batch size was 0, then I would still need 10 hours to set up the factory. Look, we shouldn't interpret the data too much, but this would be one way of doing it. So the data set I'm going to be using is the faithful data set, which is built into R. So I can load that into memory by typing data faithful here, and then I'm going to look at the first few lines by looking at the head of this data set. So here we go, and of course, if we want to know what this data set is about, we can look in the help file for faithful, which I can never spell, But here we go. It's data on the old faithful geyser data. Do you say geyser or geyser? I don't know. But whichever you like, this is the waiting time between eruptions and the duration of the eruption for the old faithful geyser in Yellowstone National Park, Wyoming, USA, which I think is where Yogi Bear lived. Correct me in the comments if I'm wrong. So we basically got how big the eruptions were against how long we were waiting. Okay, and remember if we want to see the whole data set, I can just double click up here on the top right, and it gives me the whole data set. So it's a reasonable sized data set. We've got 100 and what have we got? 272 entries here that I can look at them all. But I get the form of the data set just by looking at the head command. Okay, so let's do the linear modeling. Okay, so how are we going to do this linear modeling? So we're going to first of all plot this data before we do anything else. And if you've got to this stage, you probably may have seen this before. But the plot command, in general, in R, we're going to let's just write it down here. We're going to plot X against Y. And here we're going to plot the waiting time. So we've seen that Faithful has a column called waiting and a column called eruptions. So we're going to plot the x-axis is going to be faithful dollar waiting, and the y-axis is going to be faithful dollar eruptions. So this is the waiting from the dataset faithful. So remember, the dollar separates or tells us which column of the dataset to use, and the rest of the command here just tells us what the x label and the y label is. Okay, so if we run that first command, then let's look at this plot here. Okay, so we're finally starting to see what our data looks like. So that does look like there's a relationship, as we saw with the widgets. As the waiting time goes up, it looks like the eruption does go up. But a question for you is, well, is there a straight line here? Is a straight line model good? And we'll see how to look at that in just a moment. Okay, so I've shown how to draw this graph. Actually, if I don't run this last command, all I get is the plot. I don't get the line. Okay, but how do I get this straight line? Well, look, I'm going to tell R to do a linear model, and I'm going to use this lm command here. Okay, and this lm command is the single most useful command you'll probably use in R. It's very easy to use, and in general, the form is that you have the linear model of y against x, and you tell it which data set you want to use. It's as simple as that. Okay, so the only confusing thing is here, plot was x comma y. Okay, but here we will always put the response variable y tilde of x, where x is the explanatory variable. Okay, so we're plotting y against x, the dependent variable against the independent variable, however we call these variables. Okay, and that sometimes catches people out, so don't get too caught out yourselves. I promise you will do at some point, but maybe you're forearmed is forewarned. So we're going to do this in this example. So I'm going to plot the linear model of eruptions, which was my y data, against waiting, which was my x data. And the data set is, of course, this faithful. Okay. And all I'm doing here is I'm assigning the output of this, okay, to a variable I'm calling Yellowstone.lm. I could, if I wanted to, I could just call this foo. That would be absolutely fine. But I'm calling it Yellowstone.lm to remind me that it's something to do with Yellowstone National Park. And the .lm just reminds me that it's a linear model object. Okay, so just like anything in R, this function, this linear model function, will produce an object, and I can save it as Yellowstone.lm. Okay, so I'll run that, and that will do something. But I won't see anything until I run this last command, which is AB line. Okay, and what I'm asking R to do here is to draw a line according to the coefficients which are produced by this Yellowstone.lm object. Okay, so why am I doing that? Well, in this Yellowstone.lm $coefficients, so I can type coef or I can type coefficients. It's exactly the same. It tells me what the intercept is. It tells me what the waiting time is. Okay, so this AB line is just going to take whatever plot I have open and draw a line with that intercept and that slope. Okay, so the AB line draws this slope here. Okay, so altogether what I'm telling R to do is to draw the graph without the line, find the line of best fit, and then fit it. Okay, so first line, draw just the graph without the straight line. Third, this second line here, find the straight line, and this final line is to draw the straight line. Okay, and that's it. Okay, and this line kind of looks like it should do. It looks like what we believe it to do. There is a straight line upwards. Doesn't necessarily mean the model is a particularly good one, but we'll see that in a moment. Okay, so it confirms our belief that as we increase the waiting time, the eruption duration goes up. And I say as we increase the waiting time, of course, this is not something we can control. Okay, we can't turn the geyser on and off again. This is just something that happens every so often. So we have this straight line, and the next question is, well, does it fit or not? Okay, and in order to determine when it fits, what we're going to do is we're going to plot the residuals. Okay, so what are the residuals? Well, the residuals are a measure of how well the model fits, and essentially for every point in the data set, I'm going to calculate the distance between the data point and the straight line that I fitted. So these might be positive, these might be negative, but for each of these points, and I think we saw there were 172 points, I'm going to calculate what the residual is. So some of them are big and positive, and some of them are big and negative. Okay, so I'm going to have to calculate all these. So these residuals in some way tell me how well the model fits or not. Okay, so you can imagine if all the points were on the straight line, so if I had some data here and all the plots were on the straight line, residuals would be 0. There'd be no distance between the points and the line. If the model was a very bad fit, so we just have some random points all around here, okay, then the residuals are going to be very large. Okay, so in some senses, this straight line fits the bottom data better than it does the top data. So in R, I can get these residual plots by plotting, just doing a simple plot of this Yellowstone.lm object I defined earlier. And you'll see that if I plot in the script window at the top, that R will actually give me 4 plots here I can click through. If I want to do it at the console window at the bottom, I can do the same thing, but R will actually make me hit enter to see these 4 different plots. The only ones I'm going to consider here are the first 2 plots, okay? And what this does is it plots the residuals against the fitted value, okay? And what does this mean? Well, it means, so the fitted values are the y values of the straight line, okay? They're the values here, okay? So if we look at this point here, the fitted value is maybe 3 and a bit, and the residual is slightly above the line, so the residual is slightly positive. Okay, so if we look at our first residual plot, okay, this is probably this point here in the middle. Okay, so we have a fitted value on my x-axis of 3 and a bit, and it's slightly positive. Okay, and R will plot these residuals versus fitted values for all of the data points. So all we really have to do is we have to look at this plot, and we need to see that there is no pattern in the plot. We need to see that the residuals do not depend on the fitted values. So what we want to see in this plot is we want to see a sort of randomly scattered set of residuals with no pattern in the residuals. Okay, so there should be an equal number of points above and below 0, positive and negative residuals, and there should be no pattern as we move from left to right. Okay, I'll try as by default to draw this red line, which is sometimes helpful, but in this case it kind of draws our eyes to a potential problem here. So if we look at this residual plot, we can see that, hey, look, there's a pattern. So there's two sort of very clear sets of slopes here, okay? And this kind of corresponds to our original plot. These residuals are too high and these residuals are too low, and the pattern changes as the waiting time goes up, okay? And again here. So what I'm seeing in this Old Faithful plot is that we really have two sets of data points. Okay? We have a bunch of points down here, which are kind of randomly scattered around for low waiting times, and we have a bunch of points up here. Okay, and this is what we see on the residual plot. Okay, so what we'd like to see is no pattern whatsoever, but here we're seeing a slightly odd pattern here. Let's look at my second plot in my linear model object, and this is a QQ plot. Okay, so this will tell me whether my residuals are normally distributed, and again I don't need to go into this in too much detail, but if my residuals are normally distributed, then my all these points will lie on the straight line. And you'll see, well, in the middle they're pretty good, but in either tail there's a kind of pattern here which shows that my residuals are not normally distributed, certainly not at this top end. Okay, and again, these are things we'll come back to later. So you might say, well, why do I care about these residuals? Well, we made some assumptions when we stated what our linear model was, and you may not remember or have cared about this, but this is why we did it. Okay, so formally, when we fit a linear model, we are fitting this model. Okay, that y is some intercept plus some slope times that x plus this random bit here. And this random bit is what makes a statistical model. Okay, so for each x, y pairing, okay, so for each data point, what we're saying, and we can see it quite well here, is that, look, okay, if I have a batch size of just over 40, let's say 41, I'm going to go up to here, and this is going to be the sort of the place where I expect my response to be, but there's always going to be a little bit up and down. Okay, so in other words, all these points are not on the straight line, they're on the straight line plus or minus a little bit vertically. Okay, and that's what our model says. So these are our assumptions of our model, that our points are on our straight line plus this epsilon I, which determines how far away we are from the straight line. Okay, so the assumptions we need in order for our linear model theory to work are that these deviations, these random errors, these epsilon i's, have a mean of 0, they have expectation 0, they have a variance which is fixed, and that they are independent of each other. Okay. In other words, the errors have mean 0, fixed variance, which we call sigma squared, and are independent. Okay. So again, I'm not going to talk too much about the theory here, but do look in the comments below for a link to a book which talks more about it in much more detail. We would often assume as well that our residuals are normally distributed. So we'll often write down that they're normally distributed with mean 0 and variance sigma squared. Okay, so sometimes we're also going to assume normality, but actually this turns out not to be a necessary assumption, but it's one a lot of people make. Right, So it turns out that this model is necessary for everything to be sane in our linear modeling framework. And what we're doing when we plot the residuals is that we're checking whether this is true or not. Okay. So if we look back at our first plot, okay, we should see that our residuals, which are related to the errors we've assumed, always are on average the same distance away from the mean, okay, or rather that the mean is 0, so maybe that's okay because we've designed that, but we've assumed that the variance is fixed, and that means that on average these points should be the same distance away from the mean, so i.e. the up and down pattern should be so the amount they're above or below the line should on average be the same for each of these points. And we made this assumption that the errors are independent. Okay, and this assumption, this linearity assumption, should mean that how far each point above the line is not related to how far each of its neighbours is above the line. Okay, so these 2 points have the same fitted value pretty much, but the residuals should be independent of each other. And this is clearly not true. Okay, so if I have a residual of, say, 5, so if I have a fitted value of 5, then my residuals are all negative. If I have a fitted value of 1, then my residuals are all positive. Okay, in other words, where you are on the up and down plot on the residuals is determined by your fitted value. Okay, so what we're seeing formally is that our assumption of independence, which is one of our assumptions about our linear model, is not satisfied. Right. So to say again, we just need to look at this residual versus fitted plot, and if we see a pattern, then our assumption of independence is not going to be true. Second plot tests the normality, so we can test whether the data is normal, and here again this is likely to be a problem because my data is not particularly normal. In this case this is less of a problem, so this is not too far from what we'd like with all the points being on the straight line, but this first plot is the real problem. The third and the fourth plot we don't need to worry too much about. The third plot is really a sort of scaled version of our first one, and the fourth one we'll come back to is useful in detecting outliers, but that will be the subject of a future talk. So we've seen how to draw straight lines in R, and we've seen how to look at the residuals to see, do these straight lines fit our simple linear regression model. In future videos we'll see how to do a little bit more and to extract some information about exactly what kind of straight line in R we're drawing, and later still to see how we can improve our model.